Here with me is Manuel Milla Peinado, and I'm happy that I can introduce him in this talk now. And Manuel is a research engineer at the French-German Research Institute of Saint-Louis. And this institute is a binational institution dedicated to the research, the frame of defense and security. And yeah, maybe here also a link to Florian. And Manuel works with communication systems, and currently he studies how SDR and GNURadio can be used for his purposes. And the talk will be about an OFDM channel sounder with GNURadio. And well, when deploying a radio system, it is necessary to study the properties of the propagation channel. In the very beginning, this is something Professor Rode pointed out in wide detail. So there are two main elements that that may be characterized. It's the channel coherence and oh, I'm muted. Can you hear me?
Yeah.
Okay. I don't know where the message was coming from. Okay, good. Yeah. There are two main elements that must be characterized. It's the channel coherence bandwidth and the channel coherence time. And they are respectively related with the multipath components in the Doppler spectrum. And in this context, the channel sounder is an instrument designed to study the propagation channel by the emission of a test signal. This test signal is known by the receiver in advance. Thus, the channel properties can be obtained by analyzing how the channel has affected the signal. So knowing the channel is very, very important. The talk proposes the use of orthogonal frequency division multiplexing technique, OFDM, signals and the capabilities of GNURadio to implement a real-time channel sounder based on this transmission technique. So also a very, very interesting talk. And Manuel is going to be here, as we have been handling this also in the past. Dear audience, please state your questions in the YouTube chat. And we have pre-recorded also this video, and I'm going to hand over the camera to my video team. So please, Sebastian, play the video.
Welcome everybody to Software-Defined Radio Academy, to this online meeting. I'm Manuel Milla from the French-German Research Institute of St. Louis, and I'm going to introduce you and present you some work we did in the field of channel sounding. I carried this work along with my professor, Hervé Bourguin, for the University of Poitiers. And before we start with the presentation, I'm going to introduce you to some of the topics we're going to talk about. I first will present our research institute. I'll just give you some basic about it. Then I will introduce some concepts about which are important in every wireless communication, like multipath, Doppler, and so on. Then I will introduce the OFDM technique and why we chose it for channel sounding. And finally, I will continue the presentation by introducing you how we code this channel sounder with GNURadio, then some results and conclusions. So our research institute is just right near the border between Germany and Switzerland. It was founded in 1958. We are focused in the defense and security application, but not only. We do also civil research, and we work in really different domains, from photonics to wireless communication. And I will invite you to have a look on our website and check PhD positions, job offers, and general information. So everything is in our website. So I will start getting to the point by introducing the multipath effect. This effect is present in every wireless channel. So we have a transmitter and a receiver, and in an ideal situation, we will only receive the message from point A to point B, but as we are in a real propagation scenario, we are likely to receive some echoes, and these echoes, they are going to have an effect on the received signal. And as you can see, every one of these echoes is going to introduce a different attenuation and a different phase to the received signal. So the ideal scenario, the ideal propagation scenario between point A and point B is going to be effective for these echoes. So what a channel sounder does, which one of our objectives is going to be to characterize these echoes. The other one effect is present in every communication on every wireless channel is Doppler, which is present every time one of the transmitter or receiver moves. So what happens to this is going to appear an additional term to our equation, which is going to be like a frequency shift of each one of these echoes. So as we can see here, like the message received E in function of t is going to be characterized by a channel impulsive response, which is the objective of every channel sounder. So we're going to try to recover this information, like attenuation from echoes, its phase, the phase which they arrive, and its frequency shift. There's a different models to characterize of these parameters. We can split the problem in three parts. Like we can model the attenuation, we can model the multipath, and we can model the Doppler. And the attenuation is being modeled like there's a lot of industry standard models which provides really useful information for simulation, probably. So let's attack the attenuation one, which is characterized sometimes in frequency bands. And mostly it's because like, what we're going to do is like to know how much a signal is going to be attenuated when we send it through a channel. It can be a city, it can be a mountains, it can be wherever, it can be a stratospheric communication. So what we are modeling is just the attenuation. And there is a lot of, as I said before, there is a lot of industry standards models for this phenomenon. So why it's important to characterize the multipath effect? Because we can see like these echoes, they are going to affect the spectrum of the signal. So we can define some parameter here, like the average delay, the delay spread, and the larger this delay spread is, the bigger is going to be the influence on the frequency spectrum of the receiving signal. So it's really important to characterize this, the amplitude, so the attenuation of these echoes. And why the Doppler effect is important. So it's important because the bigger as we did with the multipath effect, we can define the average delay, and we can define a RMS delay spread. So the bigger this delay spread is, this quickly is going to change, the fast is going to change the channel with time. So the communication is likely to be more difficult. So as a summary, like what we're going to try to do with our channel sounder is to characterize in function of the attenuation, multipath, and Doppler. So what we call let scale fadings, it's the attenuation of the signal with the distance, and the small scale fadings is multipath and Doppler basically. So we can learn that multipath is going to affect the spectrum of the signal, and Doppler is going to affect how the signal behaves in time. So basically what the channel sounder does, we're going to send a signal through the channel, we're going to receive it at the receiver side, and what's going to happen is that we are going to analyze how this signal is being affected by the channel, we're going to try to extract the attenuation, the multipath and Doppler parameters of the channel. So why we can do that with software-defined radio? So the problem is challenging because we have to pass from a big instrument like this guy here to this instrument here. So obviously we're going to lose performance, but as we will see later, we can achieve like quite decent results. So now I'm going to introduce you to the orthogonal frequency division multiplexing technique and why we choose it for channel sounding. Basically, we choose to use frame-oriented OFDM. That is, we are going to set an OFDM signal, which is structured in time. And that way we can obtain analyze a signal per unit of times, as we will see later. So, why OFDM finally? Because this OFDM is like, thanks to the orthogonal principle, a wideband channel is going to be characterized by narrow band channels, which is really easy to study. So let's how we are going to do that. We're going to store an OFDM signal in a device, which is going to be the emitter side of our channel sounder, and we're going to radiate to the channel. And later we will analyze this frame at the receiver. So finally, the structure of this OFDM signal is going to be a frame part of it, which is going to synchronize the emitter with the receiver. We're going to have then we will obtain the channel frequency response, and later we will obtain the channel impulsive response. So we will use SDR and computer basically, and the emitter side can be another SDR or can be this instrument like here from Rothschild, as we will see later. So finally, as we were saying, we're going to send OFDM signals, so we need to synchronize them. So when we radiate an OFDM signal, they have a signed signed word. This signed word is going to pass through a digital filter in order to be able to select when this OFDM signal has been received. So this here we have the digital filter we will use to synchronize our signal. Basically, in blue here, you have the radiated OFDM signal to the channel, and in green, you have the response of this filter. So as we can see, like this filter is going to give a huge peak when every time an OFDM signal has been received. So we just need to code a GNURadio block to identify these peaks. And finally, we will additionally, this filter will give us an information of the carrier frequency offset, which contains the Doppler of this receive. So here is our synchronization block, like the image of it. Here we code some examples. So this is an example flow graph of how it works. Here we have the file source, which contains the radiated OFDM frames. They are pre-recorded for the generation of this example. We are going to pass it through this frame filter, and then we can analyze how this blocks works. So here we have the receive OFDM signals. Here we have the carrier frequency offset, and finally, in the bottom of the screen, we have the response of the filter. So as you can imagine, like later we will analyze these peaks in order to retrieve these OFDM frames. Finally, how this another block we code. So once we have synchronized of our OFDM signal, we have to extract the OFDM symbols in order to perform channel sounding. So this is going to be the work of this GNURadio block here, which basically he's going to use the information from the previous block. It's going to use the previous block is going to give us this the best estimation instant, and we are going to extract the OFDM symbols in order to perform channel sounding. So we coded this block basically. Previously, we code a digital filter. This block here was coded as a state machines with 3 different states. So basically, it just gives an OFDM symbol on each one of its outputs. So after having obtained the symbols, we have to perform we have to obtain the channel frequency response of the channel, which basically we are receiving here the E decay, which represents how the channel behaves at each one of the subcarriers of the OFDM signals, and then we have the receive one here. So basically, for each one of the received frames, we have one channel frequency response, which is the average between the 8 sent OFDM symbols contained in the test frame. And one of the effects I want to introduce you is like so far we have been working with ideal signals, like what happens when we receive an OFDM signal which is perfectly synchronized between the emitter and the receiver, which basically is not possible most of the times. So what happens, like which is likely to happen, is like the synchronization filter is going to give us a wrong estimation or a not so good estimation when we should start the sampling of the OFDM frame. So what happens, like this is going to be an offset between the right sampling instant and the wrong one, which has a really huge impact on how the channel impulse response is obtained. So we need a method to compensate this effect. So you can see here in this plot, and the black line represents a channel impulse response which was well received, well estimated, and here you have what happens if the synchronized instant was not correctly estimated by the synchronization filter. So basically, after compensating this this phenomenon, what we are going to have is like we have a problem. We have an estimation of the receive of the channel frequency response, and we have the ideal channel frequency response that we should obtain. So basically, this is a least squared minimization problem, where it can be resolved by implementing this a GNURadio block, which implements this equation. Basically, M is a matrix which is built through the known parameters, so it can be stored in memory, and H is our estimation of the channel frequency response. So basically we just perform this operation, and we have the K parameters, which is the amplitude of each multipath component of the channel impulsive response. So here it's how our channel sounder looks in GNURadio. We have the whole flow graph. So from the synchronization part, after we extract each one of the OFDM symbols contained in the frame, we perform its conversion to the frequency domain. We compute the channel frequency response. Then we compensate the STO, the sampling time offset, and then finally we get the CIR with the channel impulse response. And finally at the end, we have the information ready to plot. So here is an example that I'm going to show you of the equipment we have at the lab. That the emitter side of our channel sounder is going to be a vector signal generator from Rhodes parts. At the receiver side, we're going to have an SDR, the extras and this 310, sorry, from Ethos Research. And we're going to have, of course, a computer to analyze all of our data, and an octo clock to better drive the clocks inside the SDR. But firstly, I would like to see you some previous results with it. Like now, we are going to compare how this channel sounding technique behaves in a real propagation scenario. For example, we can try to analyze a two-path scenario. Like the direct path is going to be a direct cable between the emitter and the receiver, and the reflected path, so the second path is going to be, we can delay our signal by passing it through a 30-meter cables, and we can compare how in frequency and in time domains, how our channel frequency, how our channel sounding works. So we compare here the performance between a VNA, so vector network analyzer, which is an instrument widely used for channel sounding, and our technique. So here we have that the spectrums, they look more or less the same, with a little bit difference here at high frequencies. And in time, we also observe like some difference. But if we compare like the cost of a vector network analyzer and the cost of a software-defined radio, like for example, the model from ES310 from Ethos Research, we see how we have a good compromise between the cost and the performance we have with our channel sounding. So what we can do with our vector signal generator, like we can define a multipath propagation scenario. So to study if we are able to recover the multipath components of this channel. So we're going to work with a standard channel model, which is from E2, which is designed to be used for indoor office simulations. So it's got of 6 propagation paths. So we have a direct signal plus 5 echoes. Each one's happening at a certain delay. So for example, 100, 200, 300 nanoseconds. And the model also gives us the attenuation for each of one of these propagation model. So here one different, we have like this model also defined how the Doppler spectrum of each one of these components behaves. But we've observed some difference between what we should obtain and what we're finally obtaining. So for this time, at this experiment, we decided to work with static paths. This is like assuming each one of the receiver and the emitter, they are static, so they are not moving between each other. So the Doppler effect shouldn't be present for this experiment. And finally, here is how the channel impulse response looks. Like here we have the direct path and the echoes. And in general, we see a good match between the theory and what we obtain with our sounder. Sometimes we observe like some of the response wouldn't be obtained, but this is because the sampling time offset, this phenomenon which is really destructive, is present, and the compensation algorithm couldn't compensate completely. So sometimes we are obtaining response which don't match the the theoretical case. But in general, the instrument works. So finally, the conclusion, we propose a channel sounding technique based on the OFDM technique. We observed that in general we have a good compromise between the cost of the equipment and the results obtained, even when we have to work a little on the Doppler effect to make it more reliable. We have seen this instrument, as we are working with HDR, they are really flexible. So we can change a lot of parameters like time and frequency resolution. We worked with with laptops. Okay, they were the performance of the laptops, they are gaming-oriented laptops, so they are really hyper performance, but they are not in cost. They are not so expensive. Okay, they are expensive, but they are still cheaper than a better network analyzer. So, and we have observed this method depends a lot between the synchronization between the emitter and receiver side. So we needed to develop a sampling time offset compensation method. And we've seen that in general it works well for static scenarios, but we need to improve it for dynamic ones. So that's what we are working at this moment. So this is the end of the presentation, and I will be glad to answer your questions.